And okay, so I'd like to thank the organizers for the opportunity to take part of this program. It's really nice. And thanks, Amina, for the opportunity to speak in this seminar. Yes, I'm afraid my talk is not going to be related to these pictures here. So, but if you avoid, then you can have a look at this. Okay, so I'll talk about simple-minded stuff. And this is going to be joint work with, well, it was already. This is a report on joint work done with David Pauksztello and David Ploog. Right. So first I'm gonna explain the setting. So this second part of my title. Okay. So one setting. All right. So I'll start with. So let T be a nice category. So what do I mean by that? I mean, I want it to be unfinite, Schmidt, and a K-linear triangulated category. So here there's a field K, and for simplicity, I'm going to assume it's algebraically close. And so it's a triangulated category. So as a shift functor, I'll denote this by sigma. This is a shift functor. And I want the categories to have a Serre functor. So what's a Serre functor? So S a Serre functor. I'll come with examples after this. So this is an autoequivalence. Of the category T, for which there is a nice duality. So there's this isomorphism. So the ohms from X to Y are isomorphic to ohms from Y to the Serre functor Y to the first subgroup. Okay, and this is D is the K duality, standard K duality. Okay, this holds for any pair of objects in a category. Okay. So Reiten and Vandenberg, they tell us that a category has a Serre functor. Yes. If and only if it has Ozon-Reiten triangles. In which case the Ozon-Reiten translate, which I don't know by tau, is given by shift -1 equals with the Serre functor. Okay, so now I'm ready to define Calabi-Yau. So for that I need an integer. So given an integer W, the category is said to be W Calabi-Yau, and I'll denote this just WCY. So this is if this Serre functor is isomorphic, it's a functor to the power of the shift functor by this integer. Okay. All right. This is a lot of technicalities, but you've seen this before. So let me give you some examples. Okay. So the main example we'll be working today is with when we're taking a cyclic here. Now the integer should be non-zero, given that one. Then we can consider an orbit category of the boundary derived category. So I'll denote this by CW. So this is the orbit category. It's a boundary derived category by this functor. Okay. So remember by this result of Wright and Vandenberg, we can write this in a different form. So you can replace S by tau's shift. So you get this. Okay. And so if this W is bigger or equal than 2, then
you have equality, but you need
Sorry, I put too many of those. Yes, yeah, thank you. So if W is bigger or equal than 2, you've seen this already. These are the classical cluster categories, so positive Calabi-Yau categories. So this is higher classical cluster categories. But we can consider W negative. And this is what I'm suggesting in this talk, to consider these ones. So this will be, so one can see that these are triangulated and W Calabi-Yau. And so we have here examples of negative Calabi-Yau categories, which will, well, I dare say classical negative cluster categories. Okay, so this is an example, but we've seen there are recent interest in this negative Calabi-Yau recently, and so they appear in Nature. Say, if you define nature to be, so for example, you can consider stable magic categories of symmetric algebras. This is Nature. These are -1 Calabi-Yau. You can. There's also recent work on this negative Calabi-Yau in a setting of Koenig-Liu modules. So you can consider this stable magic categories, stable Koenig-Liu for something called, some algebras called W self-injective. So I'm not going to explain this, but just saying that such things exist, and this is recent work by Iyama-Jin. And there's also worth mentioning also recent work on differential graded stable categories of negatively graded round tree algebras. Also negative Calabi-Yau, and this is recent work by Jeremy Brightfield. And I've actually just seen that I think he's going to talk about this stuff in the Lagoon seminar in a couple of weeks' time. So it's an advert. Okay, so yes, these things exist and they are natural constructions, and so why not? Let's study this. But yes, so in this talk, I'm going to focus on this setting for W negative. So let me just copy paste this definition of the classical negative Calabi-Yau cluster categories. So as I've said, these categories are triangulated. So this is a result by Keller back in 2005. And so he says that the natural projection functor, which I don't know by pi, from the boundary drive category to this orbit category, is a triangle functor, which induces an additive equivalence from this subcategory of the derived category in the composables. FW, I'll say what FW is, but it will be our fundamental domain of the category to the incomposables of the orbit category. So what's this FW? Fundamental domain. Okay, so here I'll denote by H to be the mod KQ. Okay, so here's a picture for the derived category. So it's hereditary. So you have the mod category and then it shifts. Okay, like this. So for W bigger or equal than 2, you've seen the fundamental domain for higher cluster category. So if you take a projective here. Okay. So let's say let's see. So this orbit here will say that some objects ahead will be equivalent to this, the same. So we can take time inverse. So I'm actually doing shift W minus 1 time inverse here, which is the same. So we have that, and then we do the shift. So let's say that this is shift W minus 1 of the projectives. Okay. So here is shift W minus 1 P, and then you do tau minus 1 of that. And so under this orbit category, this P is the same as this object. Okay, so this means that okay, this is a fundamental limit. So you have H up to shift minus W minus 2, and then the shift W minus 1 of the projectives on the fundamental domain. For the negative case, if you do the same, so you take a projective here, well, now take tau, this is shift minus 1 of some injective, and then you do shift 1 minus W of that. This puts you here. And this gives I. Okay, and so this means that this object is now the same as this one. So the fundamental domain now is going to be all these copies, and then on the shift minus W, we remove the injectives. Okay, so this will be our fundamental domain. Okay, so
there's some stuff we're missing.
Sorry, here.
You just have an additive equivalence FWC.
Say that again, sorry.
You don't need to write in unless I'm missing.
Well, no.
Just bijection. I mean,
Yes.
Yeah. It's otherwise.
Yeah. Okay. Right. So, what is the goal of this talk? So now we get to the second. So simple-mindedness and tilting. Yes. Okay, so my goal is to convince you that simple-minded theory is cluster tilting. So simple-minded. Okay, so let's be more specific. So as we've seen here, we have derived categories, and we have these orbit categories, which are, so this somehow is the non-Calabi-Yau world, and this is the Calabi-Yau world. So we have derived categories, and then we have orbit categories, cluster categories. Okay, and then, and then we have this positive and negative Calabi-Yau. So you may be more familiarized with the positive Calabi-Yau. So we have cluster tilting objects. These are really projective-minded objects, right? So this is some generalization of projective modules. And the negative Calabi-Yau world, well, we've seen in the examples, there's lots of stable module categories there. And the natural thing to study there is simple objects. So in this world, in the negative Calabi-Yau world, we're going to generalize the notion of simple-minded. So what are the objects that we study here? So here we study higher or W cluster tilting. So categories. Okay. Well, it would be nice to see what this relates to in a derived category. So there's lots of work on this, and this. So what we want to look at in the derived categories is so-called silting subcategories. Okay. Well, for doubly clustered categories, we can consider a generalization of the notion of simple-minded objects, which was considered to study simple-minded stable modular categories. So we can generalize that to so-called simple-minded systems, doubly simple-minded systems. I'm going to define this in a minute. So, okay, so simple-minded systems was lots of work with different people, but I probably mentioned Koenig-Liu in this ratios. I introduced the generalization for NEW. And this appears in the setting of the study of stable equivalences. Okay. So what would be the derived version of this? So this was what's called simple-minded connection. Okay, studied by, well, several people, but Yang, for example, and how. Okay, right. So there is a relationship between this silting in the derived category and cluster tilting sitting in doubly clustered categories. This is work by Wright and Thomas. So I'll mention actually here, back in 2012, what they say is, so let's take Q as cyclic, W bigger or equal than 2, we take this orbit category CW, and then this projection functor induces a bijection between silting subcategories. In the derived category, contained in this fundamental domain, FW. These are in one-to-one correspondence with W cluster tilting subcategory in the cluster category. Okay. So, okay, so here on this talk, we're gonna look at this relationship. Okay. So somehow a parallel of this one Wright and Thomas. I also want to mention that in general, we can define so-called weakly cluster, doubly cluster tilting subcategories. Okay. And I'll claim that the counterpart here on the negative side was something called W Riemann configuration. So essentially, so the problem here is functorially finiteness. Okay, so W cluster tilting, well, it satisfies some X vanishing condition and some kind of maximality condition, but sometimes functorially finiteness might not happen, and when it happens, for the W cluster tilting, they are functorially finite. The weakly W cluster tilting, functorially finiteness might not happen. Okay, so the difference here is functorially finiteness, but in our setting, these are actually equal, i.e. in the setting of Q cyclic and on the orbit categories. Okay, so here we're going to also ask the question whether these are equal or not. And this is going to be one of the main differences on this counterpart, which somehow, well, kind of means that simple-mindedness is a terminology which is not very fair because things are actually not that simple in this. So, but yeah, I'll explain. So I'll explain. So the point of this talk is really to explain these things. Okay, but before that, let me just tell you then quickly the definitions. So again, so I can define this more general setting. This is the setting. This is a nice category. And let S be a collection of objects and W a negative number. Well, all the objects here that we consider are going to satisfy the Schur's lemma. So they're simple, right? So I'll say that that's orthogonal. So S is orthogonal if the ohms are either K or 0, K if X equals Y with 0 elements. Okay, so Schur's lemma. Okay, so now take S to be orthogonal. So this S is a simple-minded collection. Okay, now I'll denote by SMC from now on. Okay, simple-minded collection. If it satisfies two conditions. So again, it's going to be similar to the constitutive part. So there's a next vanishing condition, and there's a generating condition. So A is X vanishing. So this means that ohm. So in this case, it's going to be, instead of positive extensions vanishing for the silting case, this is going to be negative. So I actually can denote like this. 0 for yes. And there's a generating condition, which means that the whole category can be built from this simple-minded collection if we consider the fixed subcategories. So the smallest triangulated category containing S just goes on. Okay. Right, so this is going to be our counterpart of silting. Now, simple-minded systems, what is that? So again, S is an orthogonal collection, is a W, S, and S. And so W simple-minded system for W negative. If, again, there's some X vanishing condition. So now instead of having all negative extensions, we just have some negative extensions. So so this is 0 for XY. And S unite between 1 and 1. So for W equals -1, this condition doesn't appear. So for the classical case, simple-minded system, so W equals -1 is really just the ohm vanishing condition. So just the orthogonal. Right, and then there is a generating condition. Right, so this means that T can be built from S in the following way. So we have to consider the extension closure. So I'll introduce a notation here, which I explain. Can write it like this. -1 -W. So there's some filtration. So for W equals -1, it just means that the category is the extension closure of the simple-minded system. For smaller W, then you have to consider more shifts. But what's this notation? So this cross here, XY, X cross Y, this is just the elements in the category which sit inside a triangle, where the first element is in X and the third element is in. X. Okay, and then this close brackets, this funny brackets here, this means extension closure. Okay. Okay, this.
There's a question.
But I think she just answered it.
Yeah.
Yeah.
But if I equals -1, how do you write the condition A?
Condition A doesn't happen really. So this is actually for W. Okay, so for W equals -1 is the classical notion of simple-minded systems, and there we just need orthogonality, so Schur's lemma, and the generating condition, meaning that the category is the extension closure of the simple-minded system. So this doesn't happen. So actually this thing here, it's very similar to the cluster tilting case. So I'll just put here as a remark. That may have seen this. So if C is a W cluster tilting subcategory, we're trying to make a category, then we can construct the whole category like this. And so W here is positive. And this is due to Iyama-Jin. Okay. So notice, so here we have to actually take the extension closure of S, and here we just take the cluster tilting, which in some sense is also the extension closure of C, because there's the X here is vanishing, so C is. But this makes things more difficult in our negative case, because this thing is bigger, more difficult to control. And this is what causes us problems. This is why simple-minded is not so. Okay, but so I still need to define the Riemann. Okay. So it's 4. So S is W Riemann configuration. If so, remember, so this is, so here for simple-minded system we have an X vanishing generating. For the W Riemann, this should be like the weakly cluster tilting, so it's an X vanishing, but a maximality condition instead. So again, this is the same condition as above. Vanishing. B. So this now is maximality. So here we have so if you have an object in the category T for which this extension, this negative extension vanish, so this equals 0 equals shift I T X. So X in S, and this I between this interval 0 and -W-1, then this object is 0. Okay. So this is a maximality condition, and so we can relate W Riemann and simple-minded system in a similar way of weakly cluster tilting and cluster tilting. So theorem. So S is a W simple-minded system if and only if S is W Riemann, and the extension closure is functorily finite in the immediate category. So let me just remind you this definition, functorial infiniteness. So what does this mean? So X is, I'll denote this by FF. Okay. So this is functorial infinite in T if it's contravariantly finite. And covariantly finite. So what does this mean? Contravariantly finite means that any object in the big category admits a right X approximation. Say alpha T. So take T. There is a map from the X in such a way that any other map from X factors through that. Okay, so this is what is a right approximation. Then you have the dual here for left. Okay, and as I said, so for in our setting, the cyclic orbit cluster categories, positive cluster categories for associated to an hereditary algebra, you always have this functorial infiniteness. Okay, so weakly cluster tilting is cluster. But here, this doesn't happen for all. So if the quiver is thinking, then yes, but if it's not thinking, then this is more problematic. And so let me give you an example, 2 examples. Okay, so first type A. Should have always an example in front. So W equals -2 here. So okay, so the fundamental domain is what? So we have the modular category, shifts, and then the second shifts, but only of the non-injectives. Okay, so this is FW, and this guy here is isomorphic to the first guy. So okay, so there's a wrapper. Okay, so simple-minded is a generalization of simple objects. So the simple objects really should be an example of such things. So let's consider these 3 guys here. So S equals simple I1, simple I2, simple I3. So this is you can see that it's a -2 Riemann configuration, and also -2 simple-minded system. Okay. The extension closure of these guys is this modular category. Okay, which is this. The shift is this. So you can see that anything in the orbit category sits in a triangle, right? Where the first object is here and the third object is there, right? So this guy here sits in this triangle and so. Okay, so you have C equals okay, so well, what about outside Dynkin? So let's take the Kronecker. And W equals -1. So here's a picture for the derived category of the Kronecker. So we have, so this is the modular category here. So of course projectives, injectives, and this homogeneous tubes. But I'm going to partition the homogeneous tubes into these joint sets, non-empty, each one. Okay, and then we have the shifts. So it's W-1, so the fundamental domain is going to be the modular category and the shifts except the injectives. Okay, so this is W. So take this lambda to be non-empty. So we can consider the quasi-simple at the bottom of these homogeneous tubes in lambda, and then the shifts. the other set. So you can see that this is going to be a -1 Riemann configuration, but it's not -1 simple-minded system. Okay, so you take the extension closure, you get all these tubes, but this is not going to be functorially finite. So yeah, so you can see here there are already some differences, and this is also, you can also see inside the derived category, this is not going to be a simple-minded collection. So the thick subcategory of this is not going to give them. Okay, so now I can state the theorem. So this is to relate simple-minded collections in the derived category and simple-minded systems in the cluster, in a negative cluster category. So okay, so again, Q is finite, okay, 6 quiver, W negative, and this. So the statement is that this projection factor from the derived category to CW induces a bijection between simple-minded collections in the derived category contained in FW and W simple-minded systems in Iyama-Jin category. Okay, so the statement is really a complete analog of the positive Calabi-Yau setting, but the proof is it's more complicated because of this. So I should say, so this is a generalization of a result by Iyama-Jin last year. So they prove that this pi induces a well-defined map from these guys, from the simple-minded collections in this fundamental domain. To this injective, well, so to these weakly simple-minded systems. Okay, so W Riemann configurations. And so they work with Dynkin case. So if here is Dynkin, then this map is a bijection. And so it gives us this result for Q Dynkin, because in Dynkin, this weakly simple-minded systems or W Riemann coincides with W simple-minded systems. But if we want to do this outside Dynkin, we have a problem, right? We have this functorially finiteness, which we have to solve. So we need a result on functorially finiteness of this extension closure. So this is the second theorem, which is useful to prove the first one, but which we believe might hold independent interest, might be used in different settings, hopefully. So, and this builds on a result by Bondarkos, which we actually do. Okay, so the setting here is finite of Schmidt, but I have to add, unfortunately, saturated triangulated texture. And it's not important the definition here. So an example which is what matters for our context is found the derived category of an algebra with finite global dimension. And so, yeah. So take the heart of a bounded T structure. I'll explain later why this theorem is important in our setting, so I might not define this way. this is the setting, then, well, this heart is functorily finite in the ambient category T, if and only if H has enough projectives and enough injectives. And this might be quite useful and also a surprising result in the sense that it relates to conditions, which in only one of them, it takes the ambient category into account. Okay, so it's surprising in that way. Okay, but why is it relevant to our case? Because of Koenig-Liu result. So what do they tell us? They tell us that take a finite dimensional algebra. I mean, this result has been proved by other people as well in different settings. So I'm being a bit unfair here. I'm not mentioning everyone, but there are other people. So let's take, there's a bijection between these bounded T structures that I mentioned. In DBA. With a heart such that the heart, so this is heart, is given to a modular category for some algebra. And there's a bijection between this and the simple-minded collections in the bounded derived category. Okay, so what you do is, so if you take the heart, this is the modular category, you can take the simples, the simple objects, H. But if you take a simple-minded collection, S, you take the extension closure, and this is a heart of bounded T structure. And this extension closure is a modular category. Okay, so this is what matters here for us. So because we have a simple-minded collection, then we can consider the extension closure. It, by this result, is a modular category, so it has enough projectives and injectives. And so by this result, at least when the algebra is a finite global dimension, which is true in our case because we're working with a hereditary case, we can say that this extension closure is functorily finite in T. So corollary. If S is a simple-minded collection, then the extension closure of S is functorily. And so the idea of the proof is theorem 1. So, so this result here, well, we have to consider extension closures, see if it's functorily finite or not. Well, this basically boils down to relating. This relates. The idea is to relate functorily finiteness of the extension closure of S. I should actually mention this extension closure might be different in the derived category and the extension in the orbit category. So I should put a subscript with functorily finiteness of S, the extension closure in the orbit category. Okay. So right. So basically the point here is to say that this is the result. The result is kind of a complete analog of the positive Calabi-Yau, but there are some technicalities which makes it not so straightforward. Okay. Right. So this is good. So here's another. I wanted to finish this talk by talking about some combinatorics, to say that there is some nice combinatorics also in the negative Calabi-Yau world, and with relation with to non-crossing partitions. And again, this builds on previous work, so I should mention this. So the theorem says, so take a cyclic quiver, you can consider the corresponding file group, take W to be negative, then, well, there's bijection. As I mentioned, there's a bijection between simple-minded collections and simple-minded systems. And these are in bijection with certain non-crossing partitions, which we call positive. Maybe we should have called negative, really. But okay. Positive non-crossing partitions. Okay, so this is the result. Some remarks. So this builds on generalizes special cases known before. So relationship between simple-minded systems and positive non-crossing partitions was known for the Dynkin case and for W equals 1 in some work of mine in 2012, and also for any W. Okay, notation. Change this. Here's one. Type A, work by Iyama-Jin, 2018. But there's also this work of Buan, Wright, and Thomas. They know this simple minded collections and Q Dynkin. This is Buan, Wright, and Thomas, 2012, sorry, and also mentioned by Iyama-Jin. Okay, and in fact, you can say, well, what about all the non-crossing partitions? Well, Buan, Wright, and Thomas showed that there's bijection between non-crossing partitions. So this is all the non-crossing partitions. I'll define what these are soon. And simple-minded collections in the derived category. Sitting in a wider fundamental domain. Okay, so contained in. So basically, we include the injectives in the last. So this is mod KQ shift mod KQ up to. Okay, so this result is a specialization of this. So yeah.
So the set W positive non-crossing partitions of WQ, does that come down the value of W?
It's the okay. I should. So it's W non-crossing partitions. I'll define what these are. Positive is the non-crossing partitions are dependent. I'll define this soon. But so how long do I have?
Yeah,
Now,
we can go
right?
for
I can. So maybe I'll do
6 or 7 minutes.
I can do it like in these cooking programs where I'll just show the food taken out from the oven. So I've already have this written.
Yeah.
So I'll do that, I think. Yeah. Okay. Right. So this is the definition, but then I'll show this in an example. So the setting is this. So you have a cyclic quiver, take simple modules, then you can consider the corresponding value group. This is generated by simple reflections related to simple modules. And then you take, so in order to define non-crossing partition, I need to say, we need to fix a Pauksztello element. So this is a product of all of these simple reflections in a special order, and this order corresponds to the ordering of the simples into an exception sequence. Okay, so you order the simples into exception sequence, the simples into an exceptional sequence. Take the reflections, and this is the Pauksztello element. In order to define positive non-crossing partitions, and I should say actually, the notion in Buan, Wright, and Thomas of positive is a bit different from this. But for me, it's going to be related to parabolic subgroups, and this is just a subgroup generated by a subset of the simple reflections. So what's the W non-crossing partitions? Well, this is going to be tuple of reflections. So now we actually take all reflections rather than just the simples. And we write the Pauksztello element as a product of these reflections in a minimal way. So a minimal. So this is absolute length. Okay, this L is the absolute of C written as a product of reflections. Okay, and then the positive ones will be certain non-crossing partitions, will be those non-crossing partitions for which the second part here, so W2 up to W, U2 to U minus W plus 1. This guy here does not lie in any proper parabolic subgroup. Okay. So how does this bijection go? So it's better to see in an example. So take, and again, this was already known, but we generalize this for cyclic. So take the type A. We know that the Weil group here is the permutation, the set of permutations as 5. And let's take W equals -2. Okay. So the simple reflections here will be these transpositions of this form, right? I plus 1. Okay, and then all the reflections are just any transposition. So we can order then these simples into an exceptional sequence, and we take the corresponding reflections. So we can write C like this. So it will be this cycle. Okay, but we have different expressions of C in terms of products of reflections. So for example, take this. Okay, so each of these reflections corresponds to an exceptional object here. So this will be corresponding to the simple R3. This will correspond to the modulo 1, 2, 3. This to the simple R1 and this to the simple R4. Okay. And now I'm gonna make a 3 to, so W equals -2. So I'm gonna make a -1 minus W plus 1 tuple of this, so a 3 tuple. So let's say I have this, but in such a way that the second part does not lie in any parabolic subgroup. In essence, what this really is telling us is that this part here, the objects here, are sincere. So this is another way of characterizing simple-minded stuff by characterizing just the part in the fundamental, this part of the fundamental domain. So what we do here is that, so this object, the last object, goes to the modulo category. This part here goes to the shift. This part goes to the last part. Okay, so T4, this means is a simple F4. This is the shift of 1, and this is shift of 1, 2, 3. Okay, so these two, and this is the shift of 3, shift squared of 3. Okay, so the tuples will tell us in which copy of the modulo category you sit on. But there's a problem here because there's a map, there's an object, and we don't want morphisms. So what we do is inside of each of these copies of the modulo category, we take the smallest wide subcategory generated by those objects. So we take here the kernel of this, so we have this modulo category, and we take the simplest. So what's in red is actually the simple-minded collection coming from this non-crossing partition. Okay, so yeah, I'll finish it. Thank you for listening.
Thank you very much. Yeah, I will first ask people in the room if they have questions. What about people in the Zoom? Are there any questions from people in the Zoom?
I'm very naive. Just what's wrong with W equals 0 and 1?
That's a good question. I think actually, don't quote me on this. Maybe is this being recorded? I think so. There's this result of Keller. I'm not sure if we're gonna have these results for W equals 0 or 1. So there's a problem. Needs to be checked.
Final.
But also, yeah, I don't know what objects do we study there? It's a bit like the gender case.
So you probably don't have a fundamental domain.
Yeah.
Like one of the two examples in mind, I can't remember if it was 1 or 0. You probably don't have a fundamental domain.
Yeah.
Okay.
So, but it is a good question because somehow what I want to sell here is that we can see cluster tilting in a wider, well, maybe there's a general framework in which cluster tilting is like a positive paragraph sense. And yes, so it would be nice to see what can we do in 0 and 1 column.
There is another question from Bethany. Can wide subcategories be added into these bijections?
Yes, in some sense, this is related to this Ingalls and Thomas, right? There's this non-crossing partitions versus wide subcategories. It's a good question. There must be something, but I don't have a precise statement on the spot. I mean, yes, there is. So there's also hidden here. There's also a relationship with silting and simple-minded. So one can ask actually. So these two sides can be related in this wider setting, but this is not so clear when we pass on to the cluster tilting versus simple-minded. So there's stuff to be understood here, and so maybe this is one of these wider questions.
Yeah, interesting question. Any other question?
I have a vague question. So when you do the non-simple reflections, they look like the strong female or the announcement. There's that.
Maybe we
It's a
should.
big question.
So what is the question? Well, I don't know. I don't know about this stuff, so maybe we should talk about it.
Any other question? Yeah, I don't see any in the room and none in the chat. So let's thank Raquel again for this nice one. Thank you everyone for attending and hope to see you